Hello, my name is Adriano. I will show you the work Study on trap levels in lanthonide 3+ doped fluoride through thermoluminescence and scamming of energy levels. Just a brief introduction about what we will see. Fluoride materials are well known for their luminescent characteristics as wide band gap, efficient energy transfer to luminescent center, and among others. The ground and excited states of lanthonide ions are typically located in the forward band and can work as traps. The lanthonide F capability to storage electron and holes have been used to play a role for TL engineering. The goals are investigate the luminescent mechanism involved in the different kind of luminescent emissions in the studied material as phosphorescence and thermoluminescence, and investigate how the lanthonide ions contribute to these emissions. Here is a timeline for some luminescent process as radioluminescence, long-lasting emission, and thermoluminescence. Initially, when the material is submitted to radiation, we can observe in many cases that the luminescence intensity increase at the initial instance due to the trapping process of electron holes at traps. When traps are full, the intensity remains constant. When the irradiation is turned off, the luminescence does not decay abruptly. They decay slowly, and we can say that this is the phosphorescent emission. This is because the trapping of charge at shallow traps. Both processes can occur at room temperature. When the sample is heated at a constant routine rate, we can get the thermally stimulated luminescence. That is the trapping and recombination of charge located at deep traps. On the other hand, charge located at stable levels at room temperature. As results, at this figure, we can observe the phosphorescence spectrum. They decay slowly that decay slowly in function of time. Note that they are the same spectrum observed at TL measurement for the sample, which is also the same as the observed radioluminescence and photoluminescence spectrum. This means that the recombination and the luminescent center are the same. So, looking for the phosphorescence curve for different dopants, we observe that behavior is almost the same. The samples were exposed to X-ray for a specific time, and after turned off, the luminescence for the main emission was observed, and the behavior was the same for the single dopant samples with terbium, neodymium, and thulium. The only observed difference was in the initial intensity of decay. So, the defects present in the sample were firstly investigated using TL technique. Firstly, we did TL measurement in undoped sample. Was observed isolated peak centered at this temperature. According to Amaral and co-workers, this material has an intrinsic defect like a barium fluoride pseudochotic that induces a formation of a barium vacancy and two fluorine vacancies. The cover fitting method was used to get the kinetic parameters. The fitting well representing the experimental curve, and the activation energy was found to be around 0.5 electron volts. Here is a comparison of TL curves for undoped and doped samples with different lanthanide ions. We can note that the position of the main peak for the left side. Additionally, in the erbium doped sample, it's easy to observe that this sample shows the peak from the host and a new peak at a minor temperature than the other dopants. To elucidate the number of peaks at each sample, we have also used the curve fit method. Some interesting characteristics were observed. First, all doped samples presented peaks centered at the same position of the host, and new peaks can be attributed to extrinsic defects created by the lanthanide levels. Here is a table to comparing the kinetic parameters obtained for the all samples. Note that the host peak at around this temperature changes slightly the activation energy for neodymium, praseodymium, and thulium. The activation energy is almost the same for terbium and erbium, especially for erbium, that the unique doped, especially for erbium, the unique doped sample that the host peak is not overlaid by the new peaks. So, up to now, we know that intrinsic defects as F and V key centers are responsible for the host TL peak. However, if the mechanism is due to electron or hole releasing, is an open question. We also know that lanthanide dopants induce the presence of new TL peaks. Then they can act as traps. But the exact recombination mechanism is also an open question. To help us map the location of lanthionide levels in the host, we have used photoluminescence at VUV range to identify some parameters as external energy, host absorption, 4F5D1 transition, and for the lanthionide ions at this roast. Here are the measurements for praseodymium terbium doped ions. The host absorption energy was found to be around 11.7 electron volts, and the external energy was 10.2 electron volts. The same analysis was done for the other dopants, thulium, neodymium, and erbium. The 5D levels for all the samples were identified. Using the information from the photoluminescence, we have applied it in the host referred by the energy model developed by Peter Dorenbos. In the full energy level diagram showed in the figure, the zigzag curves labeled as A and B represent the ground state's energy levels of the trivalent and divalent ions, respectively. The curves labeled as C and D represent the lowest 5D states of trivalent and divalent lanthionide ions. The calculated and experimental values for the first 5D 4F transition are shown in this table. Note that the values in a good agreement. So, according to Professor Adriano, the lanthionide levels located just below the conduction band and just above the valence band can work as shallow traps and host traps, and that the levels located more distant at this region can work as deep traps. And then, take into account the position of ground state of lanthionide 2+ and 3+, and the activation energy found from TL, we conclude that, except for terbium, the 4F2+ level work as electron traps in this sample. Then we propose a simplistic mechanism that explains the TL and phosphorescence emission in lanthionide doped barium fluoride. The holes are trapped at the lanthionide 3+ ground state, creating the lanthionide 4F. The electrons are trapped at the lanthionide 2+ levels. During the releasing process, the electrons recombine with the holes trapped at the lanthionide 4F, creating the lanthionide 3+ at excited state. F and V key centers were pointed taking into account the position of the TL peaks for undoped and doped samples. Part of these results was recently published at the Optical Materials, and we explain in more detail some of these results and discussions. As conclusion, thermoluminescence features were investigated as a dependence of the dopant ion. The main mechanism was attributed to electron releasing. The energy level diagram was used to aid the results interpretation, TL results interpretation. TL emission spectra are referring to lanthonide triplet state for all lanthonide dopants. The presence of intrinsic defects corroborates to TL proposed mechanism. I'd like to thank UFS, LNLS, LPCM for the facilities, and FAPTEC, CAPS, and CNPq that partially support this research. I would like to also to thank the research group. Thank you all for watching me.